Good morning. This is brief calculus. We're going to take a look at sections 2.3 to 2.6. So what we're covering today is, or this week, is about 4 to 5 weeks worth of material from college algebra. So I'm going to use the PowerPoint provided by the textbook company to kind of give us an overview on the things we need. Moving relatively quickly through them. If we hit something that doesn't resonate with you, that you don't quite remember, that's what we'll talk about in class to build those things up. But this all should be, is stuff that you would have had in a college algebra class. Now, it might have been a while since that class, so we'll see. So let me highlight the parts that we need. Anything you have questions on, we can deal with during class. So here we go. Chapter 2, Nonlinear Functions. So first we're going to start off with polynomial and rational functions in this section. And what is a polynomial function? Well, it has coefficients. These are these little a to the n things. Those are just numbers with x to some power. So an example, 5x to the 7th plus 2x to the 3rd plus x squared minus 8. So there it is. When we have a polynomial, so and what the thing is that the exponents will all be integers. Actually, they'll be positive integers. And these numbers in front will be real numbers. We look at the leading coefficient oftentimes, and actually we look at the leading term, the term with the largest exponent, because that tells us how the graph looks, the behavior of this particular function. So this is an x to the 7th. It will behave like other x to the 7th functions. And so today we're going to review over this. Mostly what we'll look at is thinking of this largest term. Okay, so we get them into sort of two families based upon the exponents. When we have odd exponents, x to the 5th, x to the 3rd, x to the 7th, they're all going to look like this. I call this my saguaro cactus, with one arm up and one arm down sort of look. That's how our odd functions are going to look. Again, they're not all odd functions. We talked about that last week, but with the leading coefficient being odd. Not leading with a degree, odd degree. And the degree is determined by the largest exponent. Okay. And what happens if there was a negative coefficient in front? Remember, we get a reflection over the x-axis. So if we had minus x to the 3rd, it would look much like this blue one, except this part would be coming from here. So we'll call that an x, or an x to the 5th, same thing. And then this part here would be going down. So we get this if we had a minus x to the 3rd. So they reflect. And they've got a little way to remind you about that. If we have an even degree, x to the 4th, x to the 6th, x squared, any even is the largest, then you get a U shape. They both go up. Or if we had, say in this case, minus x to the 4th, we get them both going down. Okay. Now there's stuff that happens in between here, and that's part of what the polynomial is an x to the fourth and an x to the sixth are going to be different, can be different, depending upon what happens in the middle part. But the overall shape will be a U shape up for positive, a smile, or a U shape down, a frown for negative. So we kind of went through that with quadratics. Translations and reflections, we have talked about these. Now as we get into calculus, these are not as big of a deal, but let's just explain what's going on. This is going to behave, notice the graph overall is like an x to the third graph, because of this. What's happening is we've got some addition, subtraction, adding of a negative, whatever you want to think of it, inside the function. So translations, we have things that happen inside, and that we can tell is because it's happening inside of parentheses, and we have things that happen outside the main function. The main function is an x cubed, so here's our inside the parentheses. Outside is a +3, outside is a negative. Okay, any addition or subtraction, so add or subtract, we'll either move it on from the inside, moves it left or right, and if it happens on the outside, it moves it up or down. So notice this is taking an x to the third. This part tells us it moved it up 3, and this part, whenever we're inside, I want you to think this like looking in the mirror. When you look in the mirror, everything is reversed. So anything that happens inside is sort of the opposite of what you think. So we're subtracting 2. We've got this -2. It's actually going to move it in the positive direction 2. So 2 to the right. That's one thing. Whatever happens inside the function is backwards of what happens on the outside. The outside is sort of what you would think. Adding raises it, subtracting makes it sink, go down. And then finally, this negative on the outside, when I multiply on the inside or the outside, doesn't matter, multiply by a -1, which is what's happening. When I do it on the outside, let's think what's happening. On the outside, it's affecting y, so positive y's become negative y's, and negative y's become positive y's. So inside affects the x, which means a reflection actually about the y-axis. That's not what we have here, but I just want to and then if it's on the outside like the one we have, it's going to affect the y, which will reflect over the x-axis. And that's one of the things you just have to get used to with a coordinate system, is the y-axis actually has the equation of the y-axis. It's a vertical line. It's actually x equals 0. Okay, and so when x's change, it goes over the y. The x-axis is actually a horizontal line, so it's got the equation of the x-axis is actually y equals 0. And so when y values change from positive to negative, that's where it's going to do. It's going to reflect over the x-axis. So there's these kind of intuitively backwards things. If we go with our intuition, and so it just doesn't feel right, but it's how the system is when we define it. Okay, so there's all that going on with translations. We're going to see this will kind of carry through. So we're asked to graph this, and again, what we do is we start with an x to the 6th, which would again be some kind of a U shape, right? We've got a negative on the outside, and what we're doing is, because the negative's out here, we're actually, I mean, we could have written it this way, we're actually adding 64. So, you know, to graph this is going to get moved up 64, right? So we go like that. But then this negative on the outside is going to flip it. Or does it flip it first? Probably flips it first and then moves it up is the best, because you've order of operation, we would do the negative part first. Because yeah, if you flipped it now, you'd be way down here. But so what I should have done first is order of operations, flip it down like this, right? So this is the negative x to the 6th, and then when I add 64, let's erase this part, it's just going to move the whole thing up in its current orientation. So this would be minus x to the 6th plus 64, or either way. So that's just an example, and they got it there. Okay, so they did it for us. When we're graphing polynomials, one of the things that are important are these parts in between. So we want to find zeros, which are x-intercepts. And again, because the x-axis itself is some kind of a boundary place, it's the boundary between positive and negative y's. It could mean the difference between profit or loss. But that's why oftentimes, you know, in business situations, these zeros are important. It's where we go from breaking even to making a profit, or the other way around. So we look for these. Again, with Desmos, it's real nice. Once we graph it, those will show up. Also, we're interested in y-intercepts at times, again, because that's what we start with. That's when x is 0. So those are y-intercepts of value. What we're going to do a lot in calculus is we're going to look at minimums and maximums. So we've got minimums are here, a min, and we've got maximums over here. Okay, so those are things. Those can be found algebraically, and hopefully with the graphing calculator we will use those. And again, with Desmos, it's very easy. You just click on those points and that'll be there. And again, I can show you with various graphing calculators how to do that if you don't remember or maybe never learned. And one of the things we can do is the reason they know the number of degrees is you can count it by how many times it turns. So like on this, they say it's a degree 6. Notice it goes 1, 2, 3, 4, 5, 6. So I'm just kind of tracing along. I'm going down. There's 1, and I go up 2, 3, 4, 5, 6. So however many times I change places gives me my degree, right? 1, 2, 3. And they're going to give a definition, and I don't like the definition because they well, I'll show you when I get there, but the way they use it, they mix their variables. But if you just do that, looking at a graph, you can tell. Now this is a minimum number. It could actually be degree 8. Sometimes that might get hidden. Some of these are like multiple zeros and such, but we can at least look at this. We know it's at least a degree 6. Okay, and this is at least a degree 3. That's all we can really say about them. And that's what they talk about, identifying degree, how many times it changes places. So this one, 1, 2, 3, 4. They're both going up. We know it's even. 4 would make sense. Again, 4 is a minimum. This is a minimum degree 4. Okay, and again, I just count it by how many times it changes. 1, 2, 3, 4. And what you'll see is that there's the potential, if this was down, there would be the potential for 4 zeros. Four times it crosses the x-axis. Yeah. it's only crossing 2, but then there's these two. There's actually imaginary ones, right? If this was crossing here, we could get across. So we would have got 1, 2, 3, 4. Say if this came down like this. So with a 4th degree, there are potentially 4 zeros. X squared could potentially have 2. X to the 3rd could have 3, so forth and so on. And again, here's another one, and we'll just say that that's 1, 2, 3, 4, 5. And we can see it's an odd. One's going up, one's coming down, that little saguaro cactus thing. So we call that the 5th degree. And again, 1, 2, 3, 4, 5 possible places where it could have crossed the x-axis. And this is what I'm talking about. Notice they use the n, so it has a degree of n, and it has this many turning points. And I don't count the turning points. It's where they count the minimums or maximums. I just count how many times it changes direction. So, and then they switch over, and then they use n for the number of turning points. So it's confusing. So if you see that in the textbook, ignore it. It's not right. They're using n in 2 different ways, as the degree and then as turning points, and they should use a different variable. Okay, and it gives some things that if we have an even degree, both go up or both go down. So this is an even, either this way or this way, and then if it's odd, we get that saguaro cactus, right? So this is our odd degree, or it could be the other way around, and that's what this talks about, is the graph. You just really have to focus on what happens as x is getting big positively. If it's going up, then it's going to be positive, right? So these are going to have a positive leading coefficients, and if the positive x direction, right, over here, if it's going down, as in this one or this one, then that's when it's going to be a negative leading coefficient. And again, we're just going through mostly review. Rational functions. Now they usually use p of x, d of x. I like to use numerator over denominator. And we can, basically, what is the numerator? It is some function in the top, some function in the bottom. And as we look at rational functions, knowing what the numerator is, the numerator controls certain things. What the numerator controls is zeros, which are, remember, x-intercept zeros. That comes from the numerator. Whenever the numerator is 0, that's going to be a 0, because it's 0 over something, right? That gives us a 0. Right? Y is equal to this. Y is equal to 0, not x. We also have things, well, when the denominator is equal to 0, right? That's undefined. And remember, from lines, slope is undefined when we divide by 0. So that's our vertical, and we get vertical, what we're going to call vertical asymptotes. Okay, that's when the denominator equals 0. And what's an asymptote? Asymptote. I have to put that P in when I go to spell it. It's when the line comes close to it. Now, they can cross. We're going to look at some examples and some different things, but it's basically as a line comes, close to it. That's what's called an asymptote, and we'll see how that works. So again, you could see when x is equal to 0, we get it would be undefined, and so there's a vertical asymptote here at actually x equals 0, which is the y-axis. The y-axis is our asymptote. One side, it's shooting up to infinity, positive infinity. On the other side, it's shooting down to negative infinity. Okay, so we could say the vertical that is going to be at x equals 0. We can see also there's, with the rational functions, you get oftentimes a horizontal asymptote, and we're going to see that that depends upon the relationship between the numerator and denominator. In this case, the denominator's degree is larger. It's x to the first, and up in the top it's x to the 0. And so our horizontal is going to be y equals 0. Horizontal asymptote. Okay, so again, we just need to be able to identify those things. That's and there's three things that could happen with the horizontal asymptote. So we've got the numerator over the denominator. So we'll talk about this y equals 0. We're going to get this y equals 0 whenever the denominator's degree, right, the degree of the denominator is bigger than the degree of the numerator. Then we get a horizontal asymptote at y equals 0. If the numerator happens to be bigger than the denominator, so we got some like x to the third over x, right? This is going to shoot off to infinity, and there is no horizontal asymptote. It doesn't stop. In the long run, it goes off to infinity. This one, in the long run, it gets closer and closer to 0. And then there's a third case where the degree of the denominator equals the degree of the numerator, and then the horizontal asymptote is going to be y equal to the ratio of the leading coefficients. So the coefficient of n over the coefficient of d. Okay, so if we had 3x to the 5th over 2x to the 5th plus other stuff, right, our horizontal asymptote is going to be y equals 3/2. Okay, so just some examples there. And so we talked about these vertical asymptotes. It's the place where larger magnitude with bound as x approaches the number k, then the line x equals k is a vertical asymptote. So that again happens when we're dividing by 0, because 0, remember, when you divide by 0, what it's really doing is going off to infinity. Okay, and I talked about the horizontal asymptotes. That's as x gets large, then it goes towards y. Okay, so horizontal asymptote goes towards as x gets really big, y is going to stay there. Okay. And then there's this one thing, there's a couple questions in there. We don't get, now we looked at this x plus 1, so if you put a -1, the bottom, the denominator would become 0. So we would think there'd be an asymptote there, but if you factor the top, you're going to get x plus 1 times x plus 2 over x plus 1. So you've got the same factor. They cancel out, and so this behaves like x plus 2, you know, a linear equation, y-intercept of 2, slope of 1. However, there's this hole at -1. And I've never gotten a really good explanation of it, but if this is our original, we can't plug in -1 because it's undefined, so that gets taken out of the domain, and the graph just looks like this. But if you graph this, this is what you'll see. You probably won't see this hole because on a graphing calculator they don't have a marker for it. It looks like just the line x plus 2, but if you look in the table of values, what we get is, in our table of values, we'd have x, we'd have y, and it would look very much like x plus 2. So at 0 it would be 2, at 1 it would be 3, but at -1 back here you would see error or undefined, because that's what it is. Okay. Graph a rational function. Again, there's many examples we'll go through, but we see the y, the horizontal asymptote, because they're the same degree, both to the first power, is going to be 3 over 2, so we get that happening. The denominator, 2x plus 4, becomes equal to 0. Subtract 4 from both sides. This is how we find our vertical asymptotes. And then divide by 2. We get x equals negative 2. And so there is our vertical asymptote, and that's how rational functions behave. In a very short time, we would, again, in college algebra, we'd spend over a week on this, maybe 2 weeks. Yeah, about 2 weeks on just rational functions alone. So we're spending a few minutes, and then we'll take some time in class. And when we do the calculus, we'll see sometimes we have functions like this. Okay, we're already on to exponential functions, and actually, in reality, we've covered in the 2 weeks we're going to cover is a whole semester course. Okay, so this is again supposed to be review. Yeah, that's what they told me when I was a kid and they put me in a swimming pool. My mom thought I was a good swimmer, so I got in advanced class and said jump in and start swimming. So I did, but I was not advanced. I was bobbing when we got to the deep end, and they had to pull me out. Okay, exponential functions. Now again, this is where I don't particularly like this book. They use a to the x. Most other places will say that a exponential function is y equals b, is what they use, b for base, right? And they use a times b to the x. Well, they're going to use a for this, so I guess, this is what we do with the letters. They're standing for numbers. There's multiple ways we can use them. But if we do it this way, and again, this could be f of x, that's what y is. So when we do it this way, the number, the coefficient, the number that's getting multiplied here, this is our starting value. And we'll see for finance, that means this is the amount we deposited. It's our investment. Over here, this is the base. And with exponentials, it's a percent change. And so the rate of change is, and so 1, what you want to think of 1 is 100%. So whatever the base is, and again, you don't let it be equal to 1, because if the base were 1, then you get the line y equals 1, horizontal. If the base is larger than 1, you get an increase. So I'm going to use b. b is larger than 1. If b is less than 1, you get a decreasing function. Okay, less than 100%, you're decreasing. Greater than 100% increase, you're greater than 100%, you're getting everything back plus more. Okay, so the rate itself, always you take your base and subtract 1. If b is greater than 1, you've got an increase, a positive value. If b is less than 1, you've got a decrease. Okay, and those basic things we're going to look at. We'll also look at a continuous change with letter E. Okay. But yes, we see increase here, a base of 2, so that's positive. It's greater than 1, it's going to increase. I think I can, yeah. The other thing we can do, again using translations, is if the exponent itself is negative, we get a reflection. And then remember, the way to think of this with a negative exponent, another way we could have written this is reciprocal. So this is like 1 over 2 to the x. Okay, which is, because you got that 1 here, it's going to behave as 1/2 raised to the positive x. So notice the base is less than 1, greater than 0, but less than 1. And here's another reflection. Again, we can think of 2 to the x got reflected. Again, it's on the outside, so it reflected over the x-axis. So this thing coming up here reflected over, and then it got moved up 3. So instead of having an asymptote, so this was the original 2 to the x. Down here, something like that would have been minus 2 to the x, and then we add 3 to it, moves it up, and this is what we get. So reflections. And again, so then the base, if 2 numbers are equal to each other, then their exponents have to be equal. So we're going to use this feature. You'll see in the homework if you're solving something like 2 to the x equals 2 to the 7th. What do you know? Well, we know that x equals 7. Now, they don't always give you these problems like this. What they'll do is they'll do something like 3 to the x equals 81. Well, how do we solve this? And I'll ask you to do it without a calculator. You have to recognize 81 is 3 times 3 is 9, times 3 more is 27, times 3 more is 81. That what we really have is we can rewrite 81 as 3 to the 4th power, so then we know that x equals 4. So they use that as a tool. Okay. We could also, if we have this, we could use a graphing calculator, graph each side and then find where they intersect, and what you'd have is 3 to the x would look like this. 81 is a horizontal line way up here at 81, and what you'd find is that where they intersected, you would have they intersect at x equals 4. So we could solve it this way. They intersect at 4, 81. And we'll do those again as we work through problems. Okay. Solve this one. Well, what do? Let's go ahead. This is a good one for a decimals. We're just going to graph both of them, and then we'll solve it that way. So let me look over here. I'm going to pause this for a moment. I guess we'll keep this because I'll post these as is. Let's see, let me get my decimals right over here. And I didn't have it smoothly come in as possible, so yeah, it's kind of, they're going to do it by hand, but I'm going to show we can do this as y equals 25 raised to the x divided by 2. So that's one graph. Then the other would be 125 raised to the x plus, oh, I want to stay up there, so I'll do x, let's see if it'll, no. So what I'm going to do is I'm going to put a parentheses, x plus 3, because notice it was dropping me down. Okay, so now I come here, and I'm all zoomed out, or zoomed in, or something. Let's see, I'm just zooming out till I way zoomed in. Let's see, here we go. Where do they intersect? Well, we can see they're both shooting up. Where they're going to intersect probably is back in here somewhere. So notice all I have to do is click on, there it shows it to me right there, negative 4.5 and 0.001. That's where they're equal. But there's also some y-intercepts, but that's the intersection point, negative 4.5. So remember that number, negative 4.5. And we'll see 9 divided by 2 is 4.5. Okay, so we'll go back to the slideshow. They go through, again, they do the thing of recognizing that 25 is 5 squared, 125 is 5 to the third. So they do this, and then they can set the equations equal. That works too, but graphing calculator also got us x equals, so this is minus 4.5. Okay, so we've got access to both tools. This is pretty important for finance folks. Simple interest, even though you won't see much of that because it doesn't have the compounding effects, in modern finance, everything really is looked upon as being some kind of compounding, even if it's just annual. Now we do get simple interest in a situation where you take out the interest. Retirees will do this. They'll invest it and then they live off the interest. That's what simple interest is when you earn it, you take it and spend it. You don't leave it invested. If you leave it invested, you get this compounding effect where you start getting interest on your interest. So this is reinvesting interest here. This is if you're going to take your interest, that's simple interest. Okay. So be able to use these. And again, I don't know, this book is a little different. I'm used to having in here instead of m times per year. If you're like me, it's in times per year. Okay, so n would be equal to 12 if it was monthly. And maybe that's why they use the m. And that's what I find a lot of times in finance, they use different variables than they do in math. Of course, you all finance folks, so I'll defer to what works best for you all. Okay. One other concept is that there's this possibility of what they call continuous compounding, and that means it's not just every second, but it's like it's a process that continues continuously, and we get close to this number e, which is 2.7. I think it's 2.718. And there, again, it's a number like pi that never repeats, and the digits go on forever without repeating. But we use it. Okay, so you'll see that e is not a variable; it is actually a number, kind of close to 3, but not quite. And it's whenever we're compounding continuously, we're going to be using this PERT, P-E to the RT. Okay, and in this case, when we use it, the rate is R. R is our rate. So if it's a 3% return, it's going to be PE to the 0.03 times T. Okay, so whatever that rate is, interest rate is right here. If it's negative, then it's a decreasing rate, which isn't a good thing with money, but if we were losing 3%, that could happen. It has happened. Okay, so example, compound interest. We'll just go through this. 3.5, continuously compounded. Close to what I had. We start with 800, and we're going to do it for 4 years. So principal e to the RT. Principal is 800. E is E, it's a number, remember. The rate is 0.0315, dividing this by 100. And then you've got T, which is the number of years, so we'll have a 4 up here. And again, we may want to make sure that's all up in the exponent. And then you could calculate that with the scientific calculator. It would work. Perfect. Okay. And Desmos has those. Again, I think they do it. They put it all here. We see it, and they come up with $907.43. So it made about $107.43 in 4 years. Logarithmic functions, and again, this is just an overview. We're going to hit the high points. We'll help you with the problems, and then in class we can focus on the parts that you have questions on, working through the 50 homework problems for this week, and then the 16 quiz questions. That's what our goal is. So logarithms, they're inverses of each other. I call it the log dance. So if we have a y to the x, now watch how this happens. This one I will spend a little bit of time on. So if we have 2 plus 3 equals 5, right? That's a forward operation of addition. Now if we're going to do subtraction, what do? 5 minus 2 equals 3, or 5 minus 3 equals 2. But notice how on one side we've got these two together equals a number, and the inverse operation has as 2 come over and 1 goes over. So the one that was by itself, the 5 was by itself, now has a partner. Okay, so it changes because this is an inverse operation. This is subtraction. This was addition. Same thing happens with multiplication. 3 times 4 equals 12. The inverse operation is division, so you would do 12 divided by, say, 4 equals 3. So I call that sort of a dance. If we have the facts, and again, with mathematics, there's always 3 things. 2 things are being operated on together, combined somehow, and giving the third. So when we've got this fact, 3 times 4 is 12. It always is. We also know that 12 divided by 4 is 3. We also know that 12 divided by 3 is 4, because they're commutative. These or at least multiplication and addition is commutative, so we could do it. Exponential is not quite, but whenever we have, so if we have 2 to the x equals 8, we can do the inverse. Notice 2 and x are together. They're going to switch. They're going to be. They're not going to be together. 8's going to be together with one of these. And the way it works is the base, right, stays the base. So the logarithm has a base of 2. So that 2 goes down there. Now the 8's going to come over to it, or the 2 goes to the 8, however you want to think of it. So it's a dance. Now that's what is not 0. I don't know. Where was that 0 coming from? Sometimes it just happens. X. Okay, so notice three players are 2 and x. Those are on the same side. They come over here. So it's a what I call the log dance. So up here they show us a to the y equals x. So log base a. Notice the base stays the base. Now the a was not together with the x, but now it is when we go to the inverse. And so they switch sides. Okay, and we can use that to actually solve a lot of equations. Notice how we had this, we solved it for x just by doing a dance. We changed it into its exponential form. So the log dance, we can go with either way. Okay, and of course we get some properties. So, 3 squared equals 9 is the same thing as log base 3 of 9. So you start seeing, and it just sort of made sense to me eventually. One of my teachers was saying, a logarithm, the answer to a logarithm is just the exponent, right? Because of this log dance thing. So notice the exponent becomes the answer. The exponent is the answer. Exponent is the answer. The exponent is the answer. The exponent is the answer. Okay, so for a logarithm, so a log is saying, what is the exponent that I put on the base that gives me this? And so then they define it, a has to be greater than 0, and it can't be equal to 1 because we don't have a log base 1, because remember that would be 1 to the x, which is just always equal to 1. It's a very boring function, so we don't call it. So a is anything but 1. Now, we do write something called log of x, and we might think, well, there's nothing there, so is that a 1? No, it's a 10. If there's nothing there, it's a 10. It's a base 10. And then there's the other one is the natural log of x, which is actually log base e of x. Okay. And sometimes in finance, I'll see the switch. They'll do that log is actually what mathematicians call the natural log, and the natural log is base 10 because you're dealing with money that's a base 10. So sometimes they do that in the literature. I've seen it done, at least when I was studying. That was 20 years ago. Maybe they've changed back. But you just need to see how they define it. Okay, so in this class, it's a math class, ln will always be the natural log. So we see that an exponential and a logarithm are inverse functions of each other. So here's 2 to the x, here's its inverse. So exponentials are our fastest growing functions, logarithms are going to be the slowest growing function. Complete opposites. We have these properties of logarithms, so when we multiply two things inside a logarithm, it's the same thing as if we were to split them into two logarithms and add them. Okay, so multiplication becomes addition, division becomes subtraction. And again, there's going to be some in the homework for you to practice on these, and I'll be happy to work through a few of them, work through some examples together. This also has that the exponent comes down in front. That's the exponent rule. So notice it can drop down in front. So that's another way to expand logarithms. And then a few other things that when the base and the input are the same, that's going to be equal to 1. And when the base and the logarithm of 1 is always 0, that's because anything to the 0 power equals 1. And then finally, if you have the base and you have a base to the r, it's, again, the answer is the logarithm. The answer is the exponent. Right? The exponent is the answer to a logarithm. That's what that one's saying. So again, we're going to be applying these, and there's also a few other applications. So here's I just left this in here as an example. So if you're adding to, it can also be written as multiplying the two things inside the logarithm. And they've got a name for that. I just call them the inputs to the logarithm. So there's an x minus 1, so we can multiply. And again, oftentimes they don't put parentheses, but your calculator will make it put parentheses like that. Okay, so we've got this one. This is division of two things. We can change it to subtraction of the two things. Notice two logarithms split off. And then this one, the 5 can come down in front. And it can also, I guess they split it first. Yeah, actually it can't come here. And the reason it can't, because that 5 is not on the 9. It's only on the x. So sometimes I get ahead of myself. Let's go with the eraser. But I usually catch it later on. So we split it with addition, and then now we can take this down in front, so fully expand it out. Okay, let's look at a few. So how do we write this one? We'll go ahead and do this one. Log base a, so it's division, we'll make it into subtraction. Log base a, y to the third, and then we'll take these exponents, move them down in front. So I'm going to go over here because I think this is going to get filled up with stuff. So this is going to be 2 log base a of x minus 3 log base a of y. And sure enough, that's what they come up with, step by step. Okay, there's a change of base there. So for use, and this is helpful with calculators because some calculators do have a base. Well, let me just show you on a TI calculator. Oops. Go back. TI calculator. Okay. They didn't. The Desmos calculator doesn't have it, but this one does. Oh, I've already got it open, so let's open it up. Let's turn it on, and where it is. So if I want to do some logarithm, I can do it. Say, and let me just show you. So we did that one with 81. 3x equals 81, right? 3 to the 4th equals 81. There's also something, most calculators, if you go to the math and then you come down, they have something called log base. And what that allows you to do is put in log base. So log base 3 of 81 equals 4. Remember, that's that 3 to the 4th is equal to 81. The other way you can do it with these change of base is you could, this is log base 10 actually, right? Because there's nothing there. We do 81 divided by, again, this is a different feature, log base 3. This is a change of base. I'm now actually using a base 10 to calculate a log base 3. Notice I get the same answer. Okay, so if you have the log base, you can just enter it in as it is. You get your answer. I like that one, but some of the older calculators don't have that feature. Desmos doesn't have it yet, so you have to use the change of base formula. That's what that's for. Okay, and it works whether you're using base 10. It works with any base. So again, we can use the natural log is what's used, or we could use base 10. Okay, so oftentimes we would go using this as base 10 over log base A. Okay, so we could calculate that way. So evaluate this, and again, we can plug that in with either base 10 or natural log of 50 divided by natural log of 3. That's what they're going to do, and we can calculate and get it as accurate as we need it to be. And again, we could have used log base 10, so that would have been log of 50 over log of 3. We would have ended up at the same answer. Now each individual, the numerator and denominator, would have been different, but the result would have been the same. Okay. So exponential growth is really growth and decay is what we were doing with PERT, right? P-E to the R-T. What they're doing though is they've got this K, which is a constant. That's our rate actually. Y naught is a starting value, which is P. So they just, maybe I put it P-E to the R-T. So it's the same thing, but kind of they use it for exponential growth and decay. So radioactive substances decay over time. Populations increase exponentially. So it's just using different letters for really the same thing. We'll use P-E to the R-T when we're talking compound interest and finance. So you finance folks will work with it in this form. All the problems are really doing the same thing, exponential growth or decay this way. Okay, and again, we'll look at some examples in the homework. So e-sugar solutions growing at a rate such that 5 grams grows exponentially 18 grams after 16 hours. Find the growth function, assuming exponential growth. So 5 grams grows to 18. So we go from at time 0 we have 5, and 16 hours later we have 18 grams. Okay, we could do exponential regression on this. It will actually give it to us, But what we do know, again, is using our function that y naught, the beginning value, is 5. We have e. We've got some rate. We don't know what it is. They use k instead of r at this point, but that's fine. K. And we've got t. Okay, so that's our function. We've got 2 points. When we plug in 0 for t, we know we've got 5, so that's not going to help us too much. That's how we got this. But what we're able to do now is after 16, when t equals 16, we know that y is 18. Okay, so this is how we set them up. E to the k, and what we do know is that t is 16. Okay, and the way we solve this, divide both sides by 5. So 18 divided by 5 is 3 point something, 3.6. 15, then 3 is left over. 3 divided by 5 is 0.6. And I'll just write this as 16k. Okay. And again, one way to do this is to take the natural log of both sides. Natural log of 3.6. When you take the natural log of e, remember that's just going to be equal to the exponent, right? Natural log of 6, oops, natural log of e to the 16k is actually just equal to 16k. K, not x. Divide both sides by 16. That's our answer. Natural log of 3.6 divided by 16. We can plug it in, and let's see if I can keep that. Again, I'll use my calculator here. Natural log of 3.6 parentheses divided by 16. So our constant is 0.08. So an 8%. 8%. Actually, it shows it here. Go to the next page, it'll be solved. Yeah, why wouldn't you? See, I would. Well, they did it the harder way, I guess, but why wouldn't you just divide by 5 at the beginning? Let's see if they get the same answer we did. So we get a 0.08. Okay, so let me go down there. Let's come back to the slideshow. We'll go to the next one. Yeah, they get the 0.08. So we got the same answer. Again, multiple ways to do it. I'd like to take it a little bit easier. Okay, so we got a few problems. We don't work too many of those. Again, we get you working on finance. Now this is an important one to have, is effective rate. Okay, so if I give you a rate and I have compounding involved, the effective rate's actually just a little bit better. And the way I can do that is using this. There's a few problems that will ask you for that effective rate. You're going to want to use this formula. And it's really just you're calculating what's the growth of $1, and that's why you're subtracting 1 off at the end, because the additional above 1 is what the actual yield is. So, you know, a 5% compounded monthly actually has a yield a little bit more than 5%. Same thing with continuous. Your rates actually, you know, if you've got a 5% continuous, you use this. Let's just see that. So if I do a 5% continuous, what I do e to the 0.05 minus 1. You're going to see it's a little bit higher than 5%. I gotta get this thing to work a little bit nicer because I have to go in but that's okay. I mean, it works. E to the Clear this out. Oh, I want to clear. There we go. So all we have to do is E is a shifted natural log, second natural log e to the 0.05. Subtract 1 from that. What we're going to see it's a little bit more than 5%, 5.127%. So we would say that was over here. I guess I can't write 5.127. Okay. And they give us some examples here where they, here's compounded monthly, 4.25. They go through it. You're actually, notice instead of getting 4.25, you're actually, the yield is 4.33% effectively. So the more you compound, the higher the actual return is. Okay, and here's another example. Estimating how long it takes, again, using the formulas, plugging in what's known, getting to this goal of 50,000, and then solving for the exponent. Now you can use natural logs again, or you can graph it. We'll look at different ways to solve these. Okay, so here's one example using natural log of both sides. So it took about 16, a little over 16 years. Rounding it up to the nearest quarter. Well, and a lot of times we'll do this, and notice you're going, well, shouldn't you round it down to 16? Well, at 16 it didn't make it there. It takes at least this long, so we want to be a little bit more conservative, take longer, so they rounded it up. Okay, and we're now to the end of this week's. We've got now time in class, once you've looked at this, to work through 50 problems. You'll see they're all related one way or another to here. And I think I've discussed most of, I went through each of the 50 problems. So quadratics look like this. Remember polynomials, there's an x to the third and fifth and sixth kind of look like that. Absolute value functions, square root functions, rational functions have asymptotes. Logarithms are the inverse of exponentials. The logarithms are the slowest growing functions. Exponentials are the fastest. And those are the basics we're going to use for this week. And the next week we actually get into limits and start talking about calculus. So hopefully this all makes sense. We'll see you in class on Wednesday and Friday, and we'll work through some of the problems, the 50 problems we've got going, so that you can keep on track. So that's it.